circle, right, the circumference is actually less than 2 pi r, and you can see why this is less than 2 pi r, because this circle really has a radius of a, and r is bigger than that, isn't it? Right? Okay. So if we did this in our universe, if we drew a giant circle and measured the radius and the circumference, right, we could determine this. By the way, all attempts to do this show that Euclid reigns, that the universe is flat. Okay. And then triangles. Is he? He might be. Okay. The triangles have more than 180 degrees of angle, and we looked at that before, right? Now, this is an example of a saddle. Okay. This is something that has negative curvature, and I think I have a saddle. I made a saddle because kids were like, they didn't believe this. I'll pass this around. Please don't feel you have to like poke your finger through it. It's just plastic, and I stuck it on here and made kind of like a saddle by hitting it with a, I don't know, Bunsen burner or something like that, right? Okay. But with a saddle like this, if you draw a circle on a saddle, the circle goes up and it goes down and it goes up and down like that, and so the circumference is actually more than 2 pi r, right? And then if you draw triangles on it, the triangles are actually squinched, the corners are squinched, and so it has less than 180 degrees of angle. Here's a picture of I stole from somebody as a saddle like this. So the question is, if the universe is curved, we should be able to do basic geometric measurements of the universe, determine its curve, right? Okay. And so what they've actually done is they've actually gone out and determined this. Okay. Basically, if you go far enough away, if you look at the universe, you see this pattern, and you saw it on the W map, all that sort of speckled pattern, the background of these slides. Yes? Okay. We think we know how big these features are because we know the universe was like 0.37 billion years old when they were created, right? Okay. So we know how big they are. If we take two features whose size we know, or we think we know, it's a statistical thing, right? Can't we measure these angles? Yeah? Right? And if we measure those angles, we can actually add them up and see what the flatness of the universe is. And as far as I can tell, the universe is exactly flat. Which is like, is that a coincidence, right? Okay. And then I already talked about the density of it, right? Okay. So the question is, if it's exactly one, if the universe is exactly flat, how did this happen, right? Well, this is the last Big Bang concept I'll foist upon you here. Okay, there's a thing called inflation theory, and we're not talking about like Jimmy Carter in the 70s and gasoline and all this stuff, right? Okay, inflation theory states that the universe sometime very early on, okay, expanded very, very fast, faster than the speed of light, and that the universe is vast. Okay, so let's wrap our minds around this. Okay, the part of the universe that we can see and experience because of the limitations of the speed of light, okay, is to the whole universe. The part we can see and experience is to the whole universe as a proton is to the planet Earth. Is that very much of the universe? No, it's a proton's worth of a planet Earth-sized universe, right? And so what that means is that the universe is vast. Now, is the Earth flat? Is the Earth flat? Yes, no, I reject that. Okay. Where's the Earth? Where is the Earth?
Right there.
Oh, it's right there. It's biting me. Here it is. I am being bitten by the Earth. Is the Earth flat? But it looks flat. I'm looking out the window. It looks flat to me. Why does it look flat? Because we can see only a small part of it, yes? If we get close enough to the Earth, it looks flat, doesn't it? It's also very dark. Okay, yes? Yes? Okay? So this is the notion, is that the flatness of our universe that we see, we can actually measure with geometry, right? The reason why it looks so flat is that it is so big and that we are only seeing a small part of it. In fact, we may never know really the whole curvature of it, right? Okay, so that's, important idea. Okay, so I know you're excited about this, so let's keep going, right? Okay, so now the question is, where is all this mass? Early on, they knew that there was a lot of missing mass. Here's how they know, right? If you look at galaxies, right? Whoops, galaxies look like this. Okay, right? If you look at galaxies, they spin at a certain rate, If you look at the stars and count them, you know the mass of the galaxy, yes? Okay. Shouldn't there be a way using the same formulas you used in the last chapter to calculate the speed they should move, given the mass that's there? Yeah, you just look at them. You can look at the redshift or whatever in these things. We can measure the rate of rotation of these galaxies, and we know how fast they're moving. How do we know the mass? Can we count the stars up, and do we know how big the stars are? Yeah, we know all that, right? Now, here's a crazy thing, is that back in the day, before they had the WMAP probe that came up with this more accurate number, they knew that we were missing like 9/10 of the mass. If you look at Andromeda, it's rotating at a rate that can only be justified with 10 times the mass that's there, right? So the question was, where's that mass? Now there's two possibilities. It could be star cinders. Aren't neutron stars hard to see? Aren't stars that never formed into stars and are just like brown dwarfs, aren't those hard to see? Yes, so maybe it's that there's things there that we can't see, and these things are called MACHOs. Massive compact halo objects, yes? Scientists have some sort of sense of humor, don't they? Not a very good one, right? Okay. This is our only hope for it to be normal matter, baryonic matter, made of protons, neutrons, stuff we know, right? Okay. And so what scientists said was, gee, if there are in the Andromeda galaxy a lot of MACHOs, a lot of massive, like, star cinders and stuff like that, right? Okay. Then we ought to be able to see them in our own galaxy. If they're in that galaxy, they should be in our galaxy, yes? And we should see them not by looking for them because they don't emit light. That's why we haven't noticed them so far. We should see them because shouldn't they block distant stars? This is how I look for pedestrians on Barber Boulevard. When I'm driving down Barber Boulevard, right, there's this crazy place between Portland and Tigard, okay, where people cross the road. They get off on the bus and they're just walking across the road in the dark, in the rain, and you cannot see them because they generally wear dark clothing. It's like this African community, and like the women wear this like ceiling to floor black robes, yes? Yeah? Okay? And you cannot see them, and they walk across in the dark. But here's what I look for. There's always traffic coming up Barber, and I look for people blocking headlights. Whenever I see somebody like going in front of headlights, I slow way down. Because even though I can't see the pedestrians because they're just all garbed in black, right? I know they're there. And I'm like, okay, if I just go slow enough, I won't run into them. Yeah? It's very scary. Okay? So what they did was they got robots basically to look at stars in the Milky Way 24/7, just all the time. Whenever they were above the horizon, they looked at them, right? If there were these star cinders, they should go in front of them, yes? Yes? There we go, and the brightness should change. Did they find star cinders? No, it's sad that they did not, because that means we really don't know what's doing this, right? They found some star cinders, not nearly enough, okay? They actually discovered like 17 types of variable stars they did not know existed, because if you look at stars 24/7 that nobody's ever looked at before because there's no particular reason to look at them, but you monitor the brightness very carefully, they've got these crazy patterns of brightness that nobody had ever looked at. Isn't that crazy? Right? Okay, so the final thing is that it's weakly interacting massive particles, or WIMPs. Yeah, there we go, right? Okay. These things are non-baryonic. We don't think that they're neutrinos. Right? Neutrinos are these very hard to detect particles, but we know what they are. We think it's something that we don't even know yet. So that can be your Nobel Prize. You can get a Nobel Prize if you discover what this dark energy is. Right? This is the lightest supersymmetry particle. Maybe it's something, there's a theory, supersymmetry, that theory that predicts that there is this particle that could account for this. We don't think they're neutrinos. Okay? We think it's something that we really haven't detected yet, which is sort of embarrassing, but there it is, right? Okay. Now, so there's one thing, right? We don't know where a lot of the mass is, right? And there are some paradoxes of the Big Bang, and this is the fun stuff, right? And the first paradox is that there can be no effect without a cause, right? So if the Big Bang is the beginning of the universe, what caused the Big Bang? Yes? This could be, right? Okay. And it turns out that this is not actually a problem, because quantum mechanics is a theory of randomness. And apparently God does play with dice, even though Einstein didn't like that notion, right? I don't know if you've heard this quote. Have you heard this quote? Quantum theory basically says that you can predict for small objects the probability of their being here or there. We can do that with ultimate precision. But we cannot predict, for example, when a particular atom's going to decay or something like that, right?